Hi, 6th grade. This video should cover chapter 15.1 from the Red Book. This is characteristics of the atmosphere. So this unit here kind of goes through the different parts of the atmosphere, what the atmosphere is made up of, and kind of why we like having an atmosphere. So I've already filled in the notes, but I'll probably redraw some of these drawings or explain them a little bit better. So the atmosphere is a mix of gases around the Earth. It is all of the gas that goes from the surface of the Earth up into the sky. And gravity is the thing that's holding these gases in place. So that's what it says right here. Right, that gravity is holding these gases in place. So as you can see over in this drawing over here, right, there's the Earth and there's me, apparently a giant on the Earth. And all those dots are gas particles. So different molecules of gas. It might be nitrogen or oxygen or argon or who knows. The point is the Earth's gravity is holding these gas molecules in orbit. It's not letting them float off, right? If gravity stopped all of a sudden, all of these individual particles would just float off in whatever direction because there would be no gravity holding them there. Outside of this reach here, right, outside of that last ring of gas particles, you're outside of the atmosphere. And the reason that there's a kind of a space where the gas particles stop and space starts is because gravity can only hold on to these tiny little particles so much, right? They don't have a lot of mass, so they don't have a lot for gravity to interact with. Gravity's a force. We're kind of getting into physics right now, but the bigger the mass, the more gravitational pull between two objects. So these things are so tiny and have so little mass that they can only be held onto for so long. And outside of that little ring here, there's no more gases, and then you would be considered in space. I'm just going to erase that stuff. The purpose of the atmosphere, at least from the perspective of humans and living organisms, is that it protects us from radiation. Right? The sun shoots out radiation. We're going to talk about that word a little bit more in a minute. It also retains heat. All of those gases that are in the atmosphere absorb heat from the sun. This is a good thing because otherwise we'd be too cold. However, if you've heard of global warming and climate change, too much heat is obviously bad. So we don't want certain gases absorb heat and retain heat better than other gases. So gases like carbon dioxide and methane, when we release more and more and more of those into the atmosphere is going to retain more heat, more than we want, and get even hotter. So this is kind of a fine balance where we retain enough heat but not get too hot. Also important is that it allows us to breathe, right? So plants produce oxygen through through photosynthesis, right? And then all organisms on Earth, whether they're plants, animals, bacteria, etc., 99% of them perform cellular respiration, which is where you take in oxygen and you essentially burn the sugars from the foods that you've eaten using that oxygen. So we need that oxygen to produce energy. Without cellular respiration and without oxygen being kind of the catalyst to that fire in our cells, in our mitochondria, we wouldn't have energy to do things. So that oxygen to us is very important. Granted, the plants that are producing that oxygen aren't producing the oxygen for us. They're actually producing the oxygen as kind of a byproduct, as a waste product, though they use it as well. A student in the last class brought up meteor protection, one that I hadn't thought of before, and I don't think the book talks about, but that's a very interesting point, right? The atmosphere, because those gases do have mass, when a meteor or a meteorite comes slamming through the atmosphere, it bumps into and slams into all of those different gases. And as it does that, it usually kind of lights on fire because of the friction, and usually burns away. So the atmosphere actually does protect us from meteors. I thought that was a really interesting point. Here we've got the atmosphere is constantly changing. So thinking about how that happens, animals and plants are breathing and performing cellular respiration, right? So photosynthesis and cellular respiration. So the amount of oxygen or carbon dioxide is always changing. The other way is through pollution, right? Through the production of different pollutants or more carbon dioxide into the atmosphere, or anything that we are producing through one of our man-made structures, right? So cars, for instance, just through their normal activity, they pollute, and therefore we're changing which gases are in the atmosphere or the makeup of those gases. So the normal composition of the atmosphere is that nitrogen is at 78%, oxygen is at 21%, and then the rest of them, argon, carbon dioxide, water, etc., 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 are less than 1% of the atmosphere. So if we start to change the amount of carbon dioxide, right, carbon dioxide should be a small percentage, right, under 1%. So if we start to bump that up closer to 1%, it's going to really change the makeup of the atmosphere, and that gas being a gas that really absorbs solar energy, it's going to start to have effects on the atmosphere and the temperature of the atmosphere. So one thing I wanted to kind of put a pause on for a second and talk about was radiation. So I kind of drew a picture here with these little hills and valleys, and we're going to talk about that. This is not something you need to write down. It's just some information so that we know what a radiation is. If I was in class, I would start off this conversation by shooting you with radiation. And I would do that by turning on and turning off the lights really fast, right? And by flickering those lights, I would be shooting you with a type of electromagnetic radiation. So radiation is just energy. Light is a form of energy. X-rays, gamma rays, UV rays, and radio waves are all types of electromagnetic radiation. There's an idea that we have that radiation is automatically dangerous. But from the light example, we know that it's, we need light. We need light to be able to see. However, if we took a really bright light and shined it directly in your eye for an hour, you'd probably go blind. So there is something there with the radiation. Some types of radiation are inherently dangerous, right? X-rays or gamma rays, you don't want to get shot by those a lot. Radio waves, not very dangerous, though after years and years and years of getting shot with them, have the potential to do some damage. So the difference is their wavelength. So all radiation travels at the same speed. It travels at the speed of light, right? Light being a type of radiation, that's just kind of the name that we use for it, but it's really the speed of radiation. However, some types of radiation, they all travel in waves, have really long waves, right? And we measure the length of the wave from the top of one wave to the top of the next wave. So this is a pretty long wave here. Other types of radiation is really short, right? And they've got these tiny little shorter waves that are much, this might be like a centimeter long. This might be, let's say 5 centimeters long. So if this one is 5 times longer, right, than this one, right, that means that the wavelength there is 5 times longer and 5 times less dangerous. The reason is because, essentially, if they're all traveling at the same speed, if you get shot by A versus B, right, if you get shot by A, in the same amount of time that it takes you to get hit by one wavelength, you're going to get hit by many wavelengths of radiation B. That's because of it being a shorter wavelength. So you're going to get hit by more of these peaks, right? If we're going to think of each of these peaks as being like an ow, 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 ow. Here you're going to get hit by 2 of those. Here you're going to get hit by 1, 2, 3, 4, 5, 6, 7, 8, 9 of those hills. So you would get hit by a lot more radiation in the same amount of time with a shorter wavelength. Just kind of going off into physics there, just to kind of give you a little bit of information about radiation. It's an interesting idea. And as you can see, in this one, and in breathing, we went off into biology. Here we're going off into physics. When we were talking about carbon dioxide, we're going off into environmental science and chemistry. So all of these things are totally intertwined. And I'm just trying to give you a broad perspective for how this all works. So the next kind of topic is atmospheric pressure and temperature. So we talked a lot about pressure in one of our previous units, and we know that pressure is force per area, right? Force divided by area. So air pressure is the pressure, or the force divided by the area, or the force pushing down on us caused by air, right? And we can actually measure that, and using pounds per square inch, which is the American way, not the best, whatever, it's 14 pounds per square inch. So if you are, this is a person, I'm going to draw him with shoulders. Right, there's his arms, there's him. So the air that's pushing down right here, and right here, and right here, on every square inch of this person's body that is pushing down, it's going to be pushing with 14 pounds right here, 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 and here, right? And then all over his head. So he can be getting pushed down by the air by hundreds of pounds of pressure of the air. That's why we actually feel like there's something pushing down on us. If you go to an area of lower pressure, you're going to feel a little bit lighter. So air pressure is just essentially that we have a mountain of air stacked up on top of us. So here's kind of a weird drawing over here. So we've got the Earth, and we've got me again. And if I'm standing here, there's this entire column of air pushing down on me, right? Like a mile-high column of air, starting at the very limit of the atmosphere and then pushing down on me and pushing down on my head. So I'm going to feel pretty heavy down here. If I'm up at the top of Everest, right, and I'm barely up there, just got one leg up on the tippy top of Everest, there's not going to be a whole lot of air above me. If there's less air above me, that means there's less air pushing down on me. So I'm not going to feel as much air pressure pushing on me. So now we're back to here. Pressure. There's less pressure in high altitude and more air pressure in low altitude, which is what we just described right there, what we just drew a picture of. That would be a good picture just to kind of visualize it, right? It's nice to be able to see it. So when we're talking about altitude, just as a reminder, it's the height of an object above a surface, right? So here, I am at altitude 0, right? I'm on the surface. All the way up here at the tip top of this mountain, right? I'm 30,000 feet above the surface of the ground, right? When we're talking about air temperature, so the air temperature changes in each layer of the atmosphere. As we go higher up into the atmosphere, the temperature changes. But it doesn't just change based on the altitude. It also changes based on the gases and how the particular gases in that layer of atmosphere absorb heat. So we could be way up here in the atmosphere where you would think that it'd be pretty cold, and it can actually be warm because the particular gases up there absorb a lot of energy from the sun. So we're going to take a look at that in the next page here. I'm going to link that, zoom down here. So here are all the different layers of the atmosphere. You know that I'm not big on memorization, so this information, we're going to want to know some of it, but it's going to be kind of quick facts. So the troposphere is the lowest layer of the atmosphere. 90% of the atmosphere's mass is contained in the troposphere. There is therefore high pressure and high temperatures down here. So we live in the troposphere, right? This is where we live. Like that. We live here. Right? So again, if we're thinking of the Earth and we're thinking of the atmosphere around it, down here there's going to be a little bit of air up here. There's probably too many dots. Right? There's going to be some air molecules up here. But as we get closer and closer to the Earth, there's going to be more and more molecules. And as you get further and further away from the Earth, there's going to be fewer and fewer molecules. Right? So that's going to explain why when you're down here, right, if you're down at this height, you're going to feel a lot of pressure. Right? There's a lot of molecules pushing down on you. It also explains why there's 90% of the Earth's mass, or the atmosphere's mass, down here rather than up here. It's kind of like a pyramid of air molecules pushing down. And the reason for that is because of gravity. Gravity pulls all of these air molecules down. And gravity, being a force, pulls them down as close to the surface as gravity can. Some of these air molecules don't get pulled down. They're still way up there, but there's a lot fewer of them up here than down here. So that's why the air pressure is going to be higher, and that's why most of the mass of the atmosphere is going to be down in the troposphere. So you come up to the stratosphere, right? So this is the edge of the troposphere. Now up here, we're in the stratosphere, right here. So the stratosphere, the air is getting thin, and it gets pretty cold because the gases up there don't absorb energy very well. However, it warms up the higher you go. So as we get higher up into the stratosphere, the gases that are up there absorb more energy. In particular, the gas that absorbs a lot of energy up there is ozone. So ozone is O3, meaning it's 3 oxygens bound together. It absorbs a lot of solar energy, and that's a good thing because it protects us. Ozone, if you've heard of the ozone layer, blocks a lot of UV radiation. So UV radiation is one of the types of radiation shot out by the sun. And the ozone layer absorbs that type of radiation. And therefore, if we have an ozone layer, we're not constantly getting shot by that much by that much radiation. But if we get rid of the ozone layer, right, there's this chemical called CFC. I don't know if you've ever heard of CFCs, chlorofluorocarbons. They're in like hairspray, right? So as you use those, they can release these CFCs and go up into the atmosphere and break apart ozone. If we break apart ozone, we get a hole in the ozone layer. That's no good, because if you've got a hole in the ozone layer, and the ozone layer is the thing protecting you from UV radiation, now you've just lost your UV radiation protection, and you can, if you're down here in the troposphere, get shot up by UV radiation. Not a good thing. One other interesting piece of information about ozone. We love ozone when it's in the stratosphere, right? Because ozone up in the stratosphere absorbs the solar radiation, protects us from the sun's energy. Great. However, when ozone is down in the troposphere, we get in trouble. Because the ozone, when it's down here, if we breathe it in, it like pings around in our lungs and creates little holes. Not a good thing. You don't want holes in your lungs. So we like ozone when it's up in the stratosphere because it protects us from the sun. But being a big, heavy molecule, we don't like it in the troposphere. Just a little tidbit of information from environmental science. Again, won't be on a test, but just interesting, I think. The mesosphere is the next layer up. That gets cold and really high winds, a couple 100 miles an hour up there. So that's where a lot of planes are flying, really, up in the mesosphere. High winds up there. The thermosphere is really far up there. Very high temperatures, up to 1,700 degrees Celsius. So that's like 3,400 degrees Fahrenheit. That's really, really hot. However, when you are up in the thermosphere, it's actually going to feel freezingly cold. And the reason why is because if you're way up here, and you're way up in the thermosphere, and this is the only molecule around here bouncing around, it's got a really high temperature, 1,700 degrees. Remember, temperature is energy, right, which is going to predict its motion. So that one molecule is bouncing all over the place. It's going crazy, right? It's the 6th grader that has had so much sugar, he is bouncing off the walls. However, if you travel up to the thermosphere, what's the likelihood that that one molecule is going to bump into you? Pretty small, right? Pretty small chance that that one molecule is going to hit you. And even if it does, it's not going to feel that hot. So, since there's so few molecules that are up in the thermosphere, there's a very small chance that you're going to have any contact with those super energized particles. So it's actually going to feel cold. So this once again comes back to chemistry and our idea that in order for any reaction or any of this stuff to happen, there needs to be contact. And if we've got so few molecules that you never come in contact with those super energized molecules, you're not going to feel any of their energy. A good analogy is like if we've got, in this room, we've got a hot tub, right? It's like 100 degrees. Feels great, nice and warm, everybody loves a hot tub. Across the state, right, out in western Massachusetts, there's a really, really hot boiling pot of water. We know that that boiling pot of water is hotter than the pool or than the hot tub. However, we are so far away from that boiling pot of water, what's the likelihood that it's going to splash on us, being 100 miles away from us? Very, very small. So even though it has more energy, it's so far away and our likelihood of coming into contact with it is super slim. But that pool or the hot tub, that we're actually inside of, right? We're in the hot tub, we're enjoying that. That's going to feel warmer than that pot of water that's boiling. So even though it's hotter, it's so far away, no chance of us coming into contact with us. So the slightly cooler pool or hot tub that we're in feels warmer. I don't know if that's a helpful analogy. Tell me in class, and I can always change it up. So the ionosphere is the last one. It's in between the mesosphere and the thermosphere. It should go right there. It absorbs X-rays and gamma rays. Thank goodness, because those are super energized types of radiation. If we were getting shot up by X-rays and gamma rays all the time, life would not exist on planet Earth. What's cool about this is that they lead to the northern lights. Because they absorb X-rays and gamma rays, they start to kind of shine in this greenish light that's really cool. So just to kind of go through and summarize really briefly, we defined what the atmosphere was and talked about why we like it, right? That it protects us from radiation, it retains heat, and it helps us breathe. We talked about how it changes constantly from breathing and photosynthesis, as well as pollution. We talked about pressure and air pressure and how it changes with different altitudes. And then we also talked about how temperature changes with altitude, but mostly because of the different gases in these different layers. So some really good test questions would be, which layer has the most mass in the atmosphere, and why? About ozone, why do we like ozone up in the stratosphere? Why do we not like ozone in the troposphere? If we're thinking about the thermosphere, this question right here is a great test question. If the thermosphere has the highest temperatures, meaning the most energy, 1700 degrees Celsius, why is the thermosphere the one that actually can feel the coldest? Right? How is that possible? That it has the most energy and yet feels the coldest. When we're back in class, please let me know if you've got any questions about any of these topics or if that analogy was not a good one.